All right, in 12.2, we're going to continue using the chi-square test, but in this case, we're going to be doing it for independence in a contingency table. So we'll still be using some of the skills from 12.1, but things are going to look just a little bit different. So the idea is we're analyzing the data between two qualitative variables. So let's look at an example. A retailer may be trying to determine whether there is a relationship between the age and where it chooses to advertise, or doctors might want to investigate whether or not a certain surgery can extend lives. Or one party in a discrimination lawsuit may be trying to show that a person's gender and pay are related. So that's what we're trying to do here is independence you can think about as like related or depends on, right? So that we can kind of make these choices. So it's pretty standard here. For a null hypothesis, we're saying that the variables are independent. And then for alternative, we're saying that they're dependent, so that they're related, they're, related or not related. Okay, that and that's oversimplifying it. We don't want to use that language, but just to help you make sense of it. So just recall a contingency table is showing those two different categories across the top. So we can be comparing brand name with age group. So let's construct the null and alternative hypothesis here, where we want to determine whether or not the age of a consumer influences their decision to buy a garment from Under Armour, Nike, or Adidas. So the null, remember the null is always independent. So what are our two variables here? Our two variables are age and brand name. So what we're saying is that age and brand are independent. It doesn't matter how old you are, you're going to buy whatever you want. And age and brand are dependent, meaning, certain age groups prefer certain brands. Okay, so that's the null and alternative. All right, so now when we go into hypothesis testing, we've talked about the null and alternative, we want to calculate, so before we get to the test statistic, which remember in the test statistic, we need like the O, the E, the O minus E, remember all that? So we need to get the expected frequencies. It's a little bit challenging to get, but it just takes a little bit of work. Once we get those expected frequencies, we're going to drop those right into there. So we'll have to calculate those, then we'll use the test statistic and the p-value. Okay. So our our expected frequencies, how we're going to get those is we are going to take the row value, multiply it by the column value, and divide it by the total, or the sample size, like the total. Okay. So in example 2 here, we want to determine, we're still talking about age and brand name. And I recall this from before. Remember that our age groups, they're down here if you forget. So they've just simplified the space. So Under Armour's B1, etc. So calculate the expected frequencies. Remember, we're going to do row times column divided by the total. So in this, and I'm just going to go like this here. Okay. So here, A1, this row, if I'm going to get here, right, I want this one first. The row value here, the row total is 396, and I can put it in here so you guys can see. 396 times the column total would be 228 divided by the total would be 600. Okay, so 396, excuse me, I think I said 398 a lot. 396, 228, and 600. This would be 396, 204, 600. This would be 396, 168 divided by 600. This would be 204 times 228 divided by 600. This would be 204 times 204 divided by 600, and this would be 204 times 168 divided by 600. Go ahead and pause this and do all those calculations. I'm going to just put them up here so we can see them. So that would be 150.48, 134.64, 110.88, 77.52, 69.36, and 57.12. So that's how you calculate the expected frequencies. So there you've got them. These are the expected frequencies, and that's how you calculate them. Now, Now that you have your expected frequencies, we're going to use the test statistic here. And so this is really similar. A couple things that are different. Our degrees of freedom is going to be calculated by, we take the row minus 1, the number of rows, take away 1, times the number of columns, take away 1. And then we're still going to do that O minus E squared divided by E, so we can still use our same column headers. And again, our expected frequencies need to be 5 or more for it to be valid. All right, so let's continue on with this example. Let's calculate our test statistic here. So for our test statistic, I've got our expected frequencies right there, all right? And so we'll do O, E, O minus E, O minus E squared, O minus E squared divided by E, okay? All right. All right, so our observed frequencies come from what we're originally given. So 174, 132, 90, 54, 72, 78. We calculated ours. Just when you're typing these in, make sure that if you go across, then you continue to go across, 110, and that your numbers match up in terms of like where they're located in the table. We're comparing the same values. All right, and just double check your E column. Everything is over 5, so we're good. And we just kind of let Excel do its magic here. Got to input a little bit of stuff, but it kind of does the heavy lifting for us. All right, and our test statistic comes from this column again. So let's sum that up. So our test statistic here is equal to, let's find it, 22.53. So our test statistic is 22.53. So that is how we calculate our test statistic. And so again here, if you want to see it all laid out, there you go. And let's continue on here. Let's actually make a conclusion. So at a 5% significance level, what can we conclude? So we need to grab our p-value. So it's the same formula for our p-value, but our degrees of freedom has changed. Our degrees of freedom, remember, is row minus 1 times column minus 1. So we have how many rows here? We have 2 rows. Row 1, 2, so 2 minus 1 is 1, times we have 3 columns, so 2, so our degrees of freedom is 2, all right? So our p-value here is squared dist t, 22.5, we could say 29 or 3, oops, doesn't, I mean, it'll make like a slight difference, but not too much, it should work out, and we get an E, right? So that means like 0.00000. So we can essentially say our p-value is, like 0.000. How does that compare to our alpha value? Well, it's less. So if the p is low, the null must go. So the independent must go. So what we're saying is that we can conclude that age group and brand name are dependent. There is evidence to suggest that certain age groups prefer certain brands, which I do think kind of makes sense. I think that, in terms of what I've seen or whatever, that we can kind of see that certain generations and ages kind of gravitate towards whatever was popular and marketed to them. So when we come back, we'll do another couple of examples, and you try.